think this works out nicely then. Okay, thank you. Okay, so first with numerical integration. Now, integrals come up all the time in economics. What is expected utility? Expected utility is nothing more than an integral. You integrate some random utility over the density of likely states or outcomes. Also, discounting utility and profits over time is really just an integration over some variable t time. Then when you get into Bayesian econometrics, the posterior is that there's the outcome of Bayesian work is a posterior density, and then to find the moments, you need to compute then the mean and variance of that density and other moments, all of which are really equal to integrals. So various integrals come up all the time as soon as you leave the simple one period deterministic models in economics. Now most integrals cannot be evaluated analytically. Yeah, the integral of x is x squared, that's nice. The integral of sine x is cosine and things like that. And the integral of e to the x is e to the x, very nice, wonderful. But that's rare. So you normally have to proceed numerically to compute integrals. Now, the first kinds of integrals, and this you all should have had in your calculus class. What you should have seen, Newton-Cotes formulas. Now, the idea of a Newton-Cotes formula is that you have some function f of x, and then you want to integrate it between a and b over this interval. And so the approach is to approximate the function f of x somehow. And this is where the approximation ideas of Tuesday come in. And then you integrate that approximation. Now, one approximation is just to take the point P and the point R, basically the endpoints, and draw a straight line. Now, by the way, that's not a terribly good approximation of the function f of x. Now, however, it's something. And then your approximation of the integral f of x is equal to then the integral under this straight line PR. Now, that integral can be done analytically. So that's one kind of integral. It's not a particularly good one. A better one is where you take 3 points over the interval AB, the endpoints, P and R, but then also include the midpoint of the interval and then evaluate the function at the midpoint, and you're at point Q. And then look at PQR. Well, PQR defines a parabola. And so parabolas can be integrated because parabolas are just second order polynomials, quadratic polynomials, and then you can integrate and you get a cubic expression. So that can be another approximation way of generating an approximation of the integral. You see, you approximate the function, and then that allows you to approximate the integral. There's another integral here. Now, another possibility here is to take the midpoint Q and then approximate the function over AB with the value of f at the midpoint. So this is just saying, well, I'm going to approximate the function f of x with this straight horizontal line. That corresponds to basically like a step function kind of approximation. You can integrate that. So here are 3 integrals then. Because step function approximation, a linear one, and then the parabolic function approximation. Okay, so that's the basic ideas. Now, the thing is that And then that generates these rules. You have the midpoint rule. My indentation here got off. The midpoint rule says that the integral of f of x over an interval is going to be, the approximation is going to be the width of the interval multiplied by the height at the endpoint. And what this says is that, this is now a theorem, this says that the error, so here's the approximation and then here's the error. And it says that there's some zeta in the interval AB such that the error equals b minus a to the cube power over 24 times f double prime, the second derivative. Now, okay, this is, yeah, so this is the simple rule. And now, and so this tells you an expression, as long as a function has two derivatives. Now, the problem is that this error is going to be large. If a is 0 and b is 100, well, 100 cubed is a big number, even when you have a small f double prime. So what instead you do is you break the interval AB into smaller intervals, each of width h, and then you apply this simple approximation of the integral to each successive interval. So you break down the integral for a to b of f of x into the integral of a to x1, and then another integral of x1 to x2, etc. So you have, and then h is the width of each of these, b minus a over n. And then what happens is that you have the approximation now is a summation of these midpoint rules, approximations. And then now notice that the error is still going to be you see, basically, why I'm missing the cube, you might say, well, now the thing is that the error was cubic in terms of each small one, but then you lost the power, but then now when you have the added, it's h squared now. So, so here's the error. Now, what's nice to see here is that the error of this formula, the error of this approximation is proportional to the square of the step size. So as you take h smaller and smaller, then the error is going to drop quadratically. Now, then we have the trapezoid rule. Trapezoid rule is where you do the piecewise linear approximation. And then the simple rule for over the whole interval AB looks like this. And then when you do a composite rule, there what happens is that the midpoint rule in the previous slide, you took an interval xi and xi plus 1, and then you just evaluate f at the midpoint. Here what happens is that any point like say x, like in an interval like x7, x8, x9, etc., x7 is going to appear twice as the right end point of x6, x7, and as left end point of the interval x7, x8. And so those points on the interior, they're going to show up twice. Now, of course, the endpoints are going to show up just once. And so now you take this, that sum multiplied by h over 2, and here you have, again, a quadratic error expression. And now Simpson's rule is where the same logic, where now you do piecewise quadratic, and there the weights go 1, 4, 2, 4, 2, 4, blah, blah, blah. But now here's the error. Now notice, however, that the errors are proportional to the fourth power of h, the fourth power of h. Now now whereas it was quadratic for the piecewise linear, so you can take the same number of nodes and get a dramatically smaller error for Simpson's rule. Now, by the way, I suspect all you have heard about is midpoint rule, trapezoid, and Simpson's rule. There are rules for arbitrary orders of approximation on intervals, degree 3, 4. Some of them have names, but they're not commonly used. There's also some numerical problems with them. Now, this may look like a nice approach. However, you've seen it, it's of limited value. And I'll show you in a few slides a far more efficient approach. Now, you might ask, well, what if you have an infinite interval, 0 to infinity, which is defined in this limit fashion? By the way, one of the funny stories about Mathematica when it first came out is that if you asked Mathematica to integrate x between minus infinity and infinity, it would say it was 0. Why would it be 0? In math courses, we're taught that it's indeterminate. Well, to physicists, it's 0. And Wolfram came from physics. Now, in math, when we talk about infinite orders, we're talking about infinite domains, and we're going to take limits. And so basically, if you're doing integration of x and the limit is the integral of x between minus a and a, well, over any finite symmetric interval, it's going to be 0, and then you take the a's off to infinity and you get 0. Whereas in reality, you've got to think of it's a double limit and it's indeterminate. These can create, Mathematica works perfectly fine now in this regard. That was only the earliest version. Now, you might think that what you should do is take 0 to infinity, and I'm going to just take some large b, and then just do my integral over that finite interval. Bad idea, because you don't know how much you're missing. Here is the mathematically legitimate way of going. What you do is you do it's nonlinear change of variables. You do a nonlinear change. You come up with some function phi, which is defined on which is defined on AB, but that its inverse is some finite range of numbers, and then you do this nonlinear change of variables. Again, this should be just refreshing your memory of calculus. And then with the change of variables, what you want to do is, if you're trying to integrate from f from 0 to infinity, you're trying to find some nonlinear change of variables so that 0 gets mapped to 0, infinity gets mapped to 1. So then so basically x here equals x to x of z. Z goes 0 to 1. And one example of that map would be z over 1 minus z. It has the properties we want, and here's x prime. And so then one way you can integrate this infinite domain integral is to integrate this over a finite domain. Now, doing a good nonlinear change of variables is, there's some art to that. And the key thing is that this change of variables is good because it's well behaved as z goes to 1 and x goes to infinity. Here's a bad change of variables, and because it creates the x of z function becomes unbounded or unbounded derivative. So there's some art to this, but nonlinear change of variables is a way to go for infinite domains. Okay, now we come to the good stuff. Again, this is good stuff, and it's classical stuff. Goes back a long ways if the name Gauss appears. Now, so what we do is first note that all integration formulas have this form. You're trying to integrate f over some domain. And what you do is you pick some points, endpoints, evaluate the function at those endpoints, and then compute a weighted sum for some set of weights, omega I. Now, the Newton-Cotes formulas that we saw use arbitrary xi nodes. Now, the examples I showed used a uniform a set of points. You could have non-uniform and just you have to adjust the formulas, et cetera. But Newton-Cotes ideas can be used for arbitrary grids xi. And then we saw how the weights come out. Now, Gaussian quadrature is the method that's based on the idea of finding the best choices, in some sense, for the nodes x and the weights omega. Okay, so it's the Newton-Cotes weights and nodes are far from being the best in any sense, and so now we're going to go find the best. Now you're going to have this term exact quadrature formula. So suppose that f sub k is a space of degree k polynomials. A quadrature formula of degree k is exact of degree k if it correctly integrates each degree k polynomial. Now, here's the magic. Gaussian quadrature will use n points, and the formulas will be exact of degree 2n minus 1. This may seem a bit strange because polynomials of degree 2n minus 1 have 2n free parameters. Now, if we wanted to approximate a polynomial of degree 2n minus 1, we would need to evaluate the function f at 2n points. That's what we learned from interpolation on Tuesday. So we have to have 2n points to approximate the function f of x exactly for degree polynomial of degree 2n. But what this says is we only need n points to exactly compute its integral. Now, here's the, okay, this is where I need a blackboard. Here's the idea. Suppose you're trying to integrate a function between -1 and 1. Now, and suppose you have a function is a sum of monomials. So let's say it's a degree 19 polynomial. So that means that there's some constant plus coefficient times x plus another one times x squared, etc. And you're integrating it between -1 and 1. Well, what's the integral of any constant over that interval? Well, if you have a constant a0, then the integral over -1, 1 is 2a0. Okay. Now, what about if the monomial term is a1 times x? What's the integral of a1 times x over that interval? Well, it's 0. The integral of x over -1, 1 is 0. Doesn't matter what a1 is. So if you have a degree 19 polynomial and you want to know what its integral is, well, you know that all the odd degree monomials disappear. So you really only have even though the space f sub 19 is of 20 dimensions, half of them don't matter. They don't make any contribution to the integral. And so you can evaluate the function at the polynomial n points and get the integral exactly. That's the logic here, is that when you're taking the integral of a function, let's say a degree n polynomial, and if it's on -1, then you know that all the odd monomials disappear. Now, when you go to arbitrary intervals, well, again, nonlinear change of variables, you're on -1, and then in the new variable, the odd powers disappear. So it's the same idea. So that's the magic of Gaussian quadrature. But now we have to find out what are the right nodes to choose and how to weigh them, so that we pick up just, it's like in a Fourier decomposition. It's like, well, we want to know some frequencies, but others we don't need to know. But we need to find out how to get some information and how to weight them. Now here's the general theorem. If phi k is an orthonormal, it means that each norm is, the norm of each basis function is 1. Orthonormal family with respect to Wx. And suppose that phi k is defined in this manner, that basically what this does, qk is the leading term of the polynomial phi k. Now let xi be 1 to n, be the n zeros of the degree n orthogonal polynomial in this family. And then let omega, so here x, this pins down the xi's. The xi's that we're going to use are the zeros of some orthogonal polynomial. The weights are equal to this expression. And then the conclusion is that these n zeros line up in order between A and B. None of these zeros are outside that interval. That's the part of the magic here. All of them are inside this interval AB. If a function is 2n times differentiable, then the error of this quadrature formula, where you evaluate f at xi and weighted by the omega i's, the error is basically equal to this number, or for some zeta, it's equal to this. So this is the 2n derivative and divided by qn squared, and then divided by 2n factorial. Now, notice basically that as long as the higher order derivatives, suppose that n grows. Now the denominator is exploding at the rate 2n factorial. So this is exploding. And so as long as the higher order derivatives do not explode as badly, or better yet, even remain bounded, this is going to be a very low error term. And this formula, this quadrature formula, is the unique formula on n nodes that exactly integrates all degree 2n minus 1 polynomials and integrates with respect to the weight w. So that's the general theory. Now, by the way, I'm not going to tell you that what you've got to do is compute all of these xi's and omega i's. The fact is that you're never going to have to do them. There's always tables to use. Now what we're going to do is here. Now we can go through a list of the quadrature rules that are related to the polynomial orthogonal polynomial systems that we talked about on Tuesday. So if you are in the domain -1, 1, and what you want to do is compute the integral of f multiplied by this weighting function, 1 over the square 1 minus x squared square root. Okay, suppose that this is the integral you wanted to use to compute. So you treat f as being some function between -1 and 1. You treat this as a weighting function. And then here's the Gauss-Chebyshev quadrature formula. You evaluate f at the n zeros of the Chebyshev degree n Chebyshev polynomial, which, by the way, is this nice convenient formula. So these are the zeros of the degree n Chebyshev polynomial. Nice formula. And then the error grows, again, goes down to 0 very rapidly for well-behaved functions. Now, okay, here's the other slide about, suppose you want to do an arbitrary compact interval. Well, then there's another change of variables you got to do. Now, here's the Gauss-Legendre quadrature. Suppose that you have the domain -1, 1, weight 1, and now then you have a formula, omega, weighted sum of the f of xi's. The error term here is, now I split this out. So suppose this is bounded, which is not a big requirement. Then what this says that the error is going down to 0 very rapidly, because this is n factorial to the 4th, and this is just basically like 2n factorial times 2n factorial. So anyway, this goes to 0 quickly. And so basically what happens is that there's this nice bound on the error. And so basically for an analytic function, a function that's analytic on this domain is going to have a bound on this term. And so then you're going to have exponential convergence. So, because, by the way, this is using the n factorial. You might think, how are you going to use n factorial here? Because that's a combinatoric thing. But then here's Stirling's rule. N factorial is approximately equal to this algebraically simple formula, and then you get these upper bounds. So this is all. So Gauss-Legendre is nice. Now, where do the zeros come from, and where do you get the nodes? Well, you always just have to look up tables, and there's multiple tables around. I have produced some, and I'll post them. So you should never find yourself doing anything to compute the weights and points for Gauss-Legendre quadrature, or for any of the next two that I'm going to show you. The tables are available, and you just list the tables. And by the way, all of these numbers are, I must have cut them off. What's the precision here? Okay. These only show 10 digits. In the tables, the tables will have 16 digits, and they will be accurate to 16 digits. Whereas if you try to use some formula and compute them on your computer using regular precision arithmetic, you'd only have 8 reliable digits. So use the tables. And here's a little life cycle example where I'm doing discounting expected utility over 50 years with this utility function, et cetera. And here's I do a 3-point Gauss-Legendre, 5-point, et cetera, with different gammas. So basically the point of all this is that as you use more and more points, things get better, which of course you know, because that's what the theory says, and no table in a lecture is going to violate the theory. Now, the next domain we're going to talk about is a double infinite domain. And this is the one with the Gaussian weight function. So this is, again, commonly seen. And here's the formula. If you're going to integrate f of x against e to the minus x squared, you have this finite sum, and then here's the formula for the error, which again is also going to go to 0 fast. Now here's the table of the quadrature nodes and weights. Notice that when you have n, by the way, when you have an odd number of points, one of the quadrature nodes is 0, the center, and then the other two will be the negative or positive of this. Okay, so that's how I got to read this, is that it's the 3-point formula doesn't have just 2 points. It's plus or minus this. And by the way, this is, I think, one of the first times you've seen this, is that when I write something like this, so this is a decimal expression, parenthesis 1. What does that mean? That means that you take this number multiplied by 10 to the 1. So this really is 1.22, etc. And so the weights in this Gaussian quadrature formula is minus 1.225, 0, and plus 1.225. That's the nodes. And then the weights are 1.18, and then 0.295, and then 1.18. And then now the important fact here is that when you go to 10-point Gauss-Hermite quadrature, so the far end points will be plus and minus 3.4. Notice the weights. The weight is pretty small. And this is the case with Gauss-Hermite quadrature, is that if you, like with a 20-point formula, the weights at the endpoints are going to be practically 0. Now, you might say that, Gauss-Hermite I can use for integrating against a normal random variable. And you're right, except what you have to realize is that the density of the normal is e to the minus, y minus mu quantity squared over 2 sigma squared. This is the density function for the normal. Now you have to do the linear change of variables to get it into the form of Gaussian quadrature in some canonical variable x. And so here's the change. So if you're computing the Gauss-Hermite, you use Gauss-Hermite quadrature to compute the expectation of a function f of y, then the formula is 1 over pi summation using those omega i's. But now then you have, this tells you what points in f to compute. So using Gauss-Hermite quadrature for expectations of normal random variables is going to require that linear change of variables, but I've done it, so it's done. That's there. Here's an example where you have a bond that's worth 1 tomorrow and an equity whose value is z, and okay, and then I compute this integral for various points. Okay. Oh, yes. Okay, now the value of the stock tomorrow is capital Z, but log of Z is normal. So the value of the stock tomorrow is log normal. And so e to the z will vary between, now little z, which is log of z, will vary from minus infinity to infinity. However, big Z, e to the z here is, e to the little z is big Z. That's going to vary from 0 to infinity. And so then this integral is well defined, because for little z equals to minus infinity, e to the little z will be 0, and so then this will be fine, and you'll be able to then compute this expectation. Now, why did I sort of fumble around for a while? See, what economists sometimes will do is have the equity value tomorrow be capital Z. You put in the normal random variable here as the value of the stock tomorrow, and then the integral doesn't exist, because 1 plus capital Z in that case could be negative. And by the way, this is a problem in much of the finance literature. For example, the Campbell approximation, Campbell and Visser approximation fails to notice this, as does work by Chris Sims and his students fail to notice this and fail to account for this. It's important to realize to understand whether or not your integral, your expected utility, is actually well defined. And again, the more points you use, the better off you are. Gauss-Laguerre quadrature, that's the weight is e to the minus x. As domain is 0 to infinity. And now, of course, this is related, obviously, to computing present value, discounted value of a cash flow. This is all, and here's your node table of nodes. And here's a simple example where, of course, things work. Now, Gaussian quadratures, you would say, okay, the theory is based on, okay, my presentation of the theory makes it sound like it's based on orthogonal polynomials and that it's only valid for highly differentiable functions. The validity of Gaussian quadrature is far greater than that. And as long as f is Riemann integrable on AB, by the way, Riemann integrable, whatever it means, it's not as, it's a stronger requirement than Lebesgue integrable. Basically, I think Riemann integrable boils down to saying that simple quadrature rules work asymptotically. Then the error in an endpoint Gauss-Legendre rule goes to 0. And so here's some, so here I take the trapezoid rule and I take and more and more points over the interval 0, 1. And of course it does this function, which is C infinity on that domain, does well. This also does well. But now this is a function that has a kink at, oh, this should be minus 1 to 1 at a negative x. And it also does well. You need more points, but it does well. So basically, Riemann integrability is all you need for Gaussian quadrature and Newton-Cotes formulas to work. Now, multidimensional integrals are much worse. One thing to do is take a product rule where you're trying to integrate over x, y, z, and so you just say, well, I'll take in the x dimension, I'll do the quadrature points in x, and then quadrature points in y, and then quadrature points in z, and then take the tensor product of those points to get x, y, z points to use. Okay, that's product rules. However, it has hideous Cursor dimensionality. So you want to avoid that for higher dimensionals functions. Now, the way to avoid those nasty Cursor dimensionality approaches is to think of monomials and how they can be pieced together to form multivariate functions. Now, this is any numerical integration formula over any domain is going to have this finite sum structure. Now, a monomial formula is complete for degree L if this approximation, if the omega i's and x super i's, points in n-dimensional space, if they add up and they exactly integrate polynomials of total degree L. Now, a total degree L is, okay, the last Tuesday, I think I got to that part where I talked about complete polynomials. The way you think about multivariate polynomials, and when you say that a monomial, that is a product of powers of x and y and z, has degree L, what that means is that the summation of the powers is bounded above by L. So x squared, y cubed, z fourth is a degree 9 monomial. You add the powers and that gives you the degree of the monomial. So, that's what you need to know. And so if you are integrating 1 over some domain and you have n points, and so then the integral is going to be a summation of the omega i's, the weights. If you're integrating just the univariate function xj over the n-dimensional domain, well then the function is going to be is going to, well, yeah, you're going to have the xi point, the point, the n dimensional point in the ith point in n dimensional space. Its jth component is then going to be the put in here, and then the weights are going to go over the omega I is going to weight over the different points I. Here you have basically this is a quadratic term between one dimension and another dimension, and here you'll be again doing this summation. Now the key thing is that the number of degree 2 monomials in d-dimensional space is roughly 1/2 d squared. And so imposing exactness means you only need to find points and their weights, d squared points and weights. So what you do is you pick some collection of points. One collection of points is just, this picture shows you a hypercube. One kind of integration formula would just say, well, okay, we always include 0, 0, 0, 0, 0. And then the other 6 points may be the centers of the faces. That's 6 more points. Maybe we want to create an integration formula that uses those. We may want to create an integration formula that uses 0, 0, 0, but then the 4 vertices. Or we want to maybe have an integration formula that uses 0, 0, and then the midpoints of these edges, or some combination. And so those are some of the ideas of how you choose sets of points. And then some monomial formulas will take combinations of these. And this is done in higher dimensions, where you pick a good set of points, not tensor product, but a nice collection of points that has some geometrical structure like that. And then you pick their weights, etc., and it works. Now, I'm not going to go into the details of this. The fact is there's a theorem due to Masovsky that says that nice monomial rules exist. Now, I'm not going to go into the details of these things right now. Later on in some of our applications, I'll refer to this, the more advanced technology on this. And by the way, one can even compute their own monomial rules by using something that we were talking about towards the end of the semester called Grosvenor bases, because finding these boils down to computing solutions to polynomial equations. This, however, is all for a topic later. Okay, so any questions on this? This is traditional quadrature. Any questions on this while I take a sip of my fluid? Okay. Now, next is Monte Carlo. Now, what I showed you before, the classical quadrature. By the way, I say numerical integration. Another term that's used is quadrature. There's also another term that's used called quadrature. Quadrature, I think, is a more general term. Sometimes you will hear people talk about integrating a differential equation. I don't like that use of the word integration. All that means is integrating a differential equation just means solving it. So you got to be careful about this jargon. But quadrature means exactly what we talked about in the first part of this lecture. Now, all of those methods, the Gaussian, the monomial, the Newton-Cotes formulas, they use predetermined points. You aim at high accuracy, but you need many nodes. Now, in economics, many people love Monte Carlo methods because what you do is you just appeal to the law of large numbers, and you say, well, I can just do a sampling of a function and approximate integrals that way. Now, and so law of large numbers, convergence, probability theory, and okay. So anyway, so that's the Monte Carlo sampling method that here's an example. Here's the theory is that if you have a random variable x or x, if you have random variables that are IID, density Q, support 0, 1, then the mean of x is the sample mean. This is sample mean is the average draw, and then the asymptotic mean of the sample mean is going to asymptotically equal this integral. So you can say, well, gee, if I want to integrate x, this function x, against some density Q of x, all I have to do is generate a lot of variables from that random draws from this density Q. Okay, that's one way of computing, approximating this integral. Now, now the limit is going to be the true value of this integral. However, the variance of the endpoint sample, the variance of the endpoint basically the variance of the sample mean after n draws is not 0. It's equal to the variance of the underlying variable divided by n. And so what that, but now you don't know what that, let's say you don't know what that variance is, you can estimate it in this fashion also. Now here's the issue. So law of large numbers suggests Monte Carlo quadrature. If you're trying to integrate this function, and right now assume that it's a uniform density, all you have to, it's equal to this expectation. So all you have to do is take n draws uniformly from the interval 0, 1, define a sample mean with n draws, and then you get this I hat is your estimate, and then there's your variance. And so I hat is an unbiased estimate of this integral. And then you say, hey, I've approximated the integral. Now, but the problem is that it does have variance. And so it has, so in this sense, the variance here corresponds to numerical error in other contexts, but it's basically the numerical error. Now, sometimes you may want to do things, and again, this is stuff that you might be familiar with anyway, antithetic variables, control variance. Importance sampling is a big deal in statistics. Things to basically reduce the variance of your approximations. Now, where do they get random numbers from? Everybody has a random number generator on their computer. However, I doubt that anybody really has a random number generator on their computer. Random numbers are seldom used. It is now possible to buy something that you plug into your laptop, and that will send the laptop a stream of random numbers. And by random, I mean their randomness is proven randomness because the device is using quantum mechanics to generate the stream of zeros and ones. Okay, so those are truly random. Now, most people can't afford those devices. A lot of people aren't even aware of it. Now, another way to get random numbers is to hire research assistants to flip coins. Well, in the United States, it's kind of expensive, and there's all sorts of work rules. They might even consider this to be abuse to hire an RA to sit around for days on end flipping coins. Anyway, so that's not a practical method either. One way is to get radioactive material and use a Geiger counter, but then you even have more issues from human relations bureaucracy about having arrays do that together, random numbers. So the fact is that random numbers used in economics research are not random. They are really deterministic sequences that look random. So pseudo-random numbers are used. And what is a pseudo-random number? A pseudo-random number is, or pseudo-random sequence, I should say, is a sequence generated in this fashion that the k+1 point is some function of the previous points. And they pass some randomness tests, not all. They are unbiased. Well, they better be unbiased if you're going to use them for integration. They have zero serial correlation. Well, that's a good idea too, particularly if you're going to use them to estimate things like variances. They satisfy some runs tests. What that means is that if you flip a coin 1,000 times, then you know that even though roughly half of the coins are going to be heads, half tails, you know that it should not look like something like heads, tails, heads, tails, heads, tails. Somewhere in those 1,000 draws, you're going to have runs of 3 heads or 5 tails. And so we test to see whether or not these sequences mimic that. Now, a statistician named Lemur said that a pseudo-random number is such where each term is unpredictable to the uninitiated mind, and digits pass a certain number of tests traditional with statisticians. By the way, Brock, Deckard, and Shankman in their work in the early 80s on chaotic sequences came up with tests for randomness. And these fail the tests for randomness. But that doesn't matter. Here's an example of one kind of uniform random number generator. Linear congruential method. The k+1 draw is equal to a times the kth draw plus c. And this is done in integers, then you mod, and then it's mod m. So this will be a sequence of integers that will generate a pseudo-random sequence if you choose A and C and M well. Eventually this will cycle because it's integers. They've got to cycle, even in theory, certainly on a computer, but even in theory they will cycle. Now, if you want a 2-dimensional set of points, you just take like draw 20 and draw 21, and well, that could be your 10th point in some 2-dimensional draw. Now, linear congruential multipliers method is a bad way. We learned that a long time ago because some other tests that don't show that they aren't really random. Now, how can they look random? Well, basically, because here's if A is a large number, so that is a slope here. So A is large means they're going to be steeply sloped. The mod M, and if this is basically real numbers now, mod 1, and so then you get chopped off. If you rise up to 1, you get cut down to 0. So you have this function, and you iterate along this line. So it's like if you're right here today, then tomorrow you're going to be up here. So you're going to get chaotic and sequences. And this is what 1,500 points generated by an LCM looks like. Now, the thing to notice here is that not only, remember, law of large numbers everybody knows about. What people tend to forget about is the central limit theorem that says that you do one of these random samples on a particular box, and you're going to get a sample of points from that box. Central limit theorem says that there's a variance. Maybe that what the true value of this should be is something like, in this case, well, like a 1/5, I guess. But you're going to have variance of that across the boxes. What that means is that there's going to be some regions where you have lots of points that are drawn. There are some regions where you have clusters, and then there's other regions where you have big holes. that are sort of inconsistent with the idea that this is a uniform sample. Uniformness in the, by the way, this is an LCM in a two-dimensional sample. Uniformness means ex ante uniformness. It means that that the probability of hitting a particular point is uniform, ex ante. Does not mean ex post uniformity. This is not a uniform set of points ex post. Here's a fancier one, more complicated one that I talk about in my book. But actually the state of the art now is something using something called Mersenne twister, which I think is available in most software packages. I think it's available in MATLAB. Now, if you want to do a non-uniform random number generator, what you do after, there's a simple way of taking, suppose your random variable has a distribution big F of X. Well, then all you have to do is compute draws from the uniform and then hit each draw with the F inverse of that point, and that's going to have a sample in with a distribution F. Again, there are special methods sometimes for these things, but basically everything boils down, typically everything boils down to doing a uniform random variable. Now, okay, I'm looking at the, okay, 10 o'clock. Now, so many times in econometrics, suppose, let's say computing the posterior mean, you're going to have some, let's say what you're going to do is compute the expectation of g of x. How are you going to, for some x parameters, and how are you going to do this is you take a random sample, draws random sample points from the domain of the random variable, and then in this case, let's say if this were a posterior, Bayesian posterior, you take a random set of points, compute the, let's say like a likelihood or posterior likelihood, and then add them up according to the appropriate weights. What is typically done is you just take random points and take and use that for your estimate. Now here's the problem is that for a lot of economics problems, the dimensionality of the integral is too high, or the economists think so. So then they love to use stochastic approximations to things such as Bayesian posteriors, and so then they they use the Monte Carlo approach. The problem is that the methods that are used do not take into account the errors of the noisiness in the whole Monte Carlo sampling process, and also there's some other features that are violated. So no, this stochastic approximation of point approach is got loaded with problems. I talked somewhat about them in later talk when we talk about applications. Anyway, so I want to get to the quasi Monte Carlo stuff. So here's an example. Suppose you want to suppose you have some function x. There's some parameter x or value x that you want to optimize, that you want to choose x to optimize this expectation. So x is, let's say, like the weight you put in a portfolio between stocks and bonds. And then the z here represents the random shocks to returns and assets. And what you want to do is choose the weight that maximizes expected utility. And now one way to do this is to take a sample z of size n, replace 8.5.1 with the sample mean. Now this is a function of x, that this variable you're trying to choose. And then you choose X to max or to minimize, this is minimization up here, to minimize this. So some people like to replace this integral with a finite number of realizations and then with given appropriate probability weights, and then minimize this stochastic approximation. Here's an example. Suppose Z is uniform and we want to find the X which minimizes Z minus X quantity squared. So this basically is find the X such, it's related to minimizing something like a variance. So, so now let's say we take a random draw, and then we, by the way, the obvious answer to this, I think, is 0.5. Yeah, the true solution to this is 0.5. But suppose we draw 3 points, and they're 0.1, 0.73, and 0.49. And it's going to end up being, the solution is going to be 0.43, not 0.5. Now, there's an error. There's noise. But now the problem is that it gets worse. I mean, it gets better, but very slowly. So here's a little portfolio example. Suppose you want to maximize your wealth tomorrow, given a safe asset has return R 1.01, risky asset is, risky asset here has normal distribution, but now I have the exponential utility function, so Z can be very negative and still this is fine. And then it turns out that for these parameters, the optimal portfolio weight omega is 1.25, which means, by the way, that you go long in the stock and short in the bond. Now, so the Monte Carlo approach would take a sample of Z's, get a finite sum, then maximize omega over that, and get some approximation to the optimal portfolio. Now, if we take what the truths, the true value is 1.25. That's what the truth is. Now, what happens if you take just 100 points? Yes, on average, you get close to 1.25, but there's a standard deviation of 0.02 for the expected, okay, no, sorry. You don't get exactly the right expected utility. Standard deviation on utility is 0.02, but the mean omega is 1.25. That may look good, but look at the standard deviation. Standard deviation is almost 0.5. So that means that a lot of times your portfolio allocation is way off. Just because you do a good job on evaluating the expected utility does not mean that you can then optimize over the omega to find out the optimal omega. You have to have 10,000 draws in order to get a standard error down to 0.05. So this is the problem with using Monte Carlo methods in a variety of contexts, portfolio optimization, maximum likelihood or moments estimation, is that you have to take an enormous number of draws to get the accuracy you need in order to then proceed with your likelihood optimization or moment minimization. Now, any questions on that? This is all, again, very fast, but much of it should be familiar to you. But I think the examples are pretty clear here. Now I'm going to talk about quasi-Monte Carlo methods. Monte Carlo methods they claim to use random sequences that satisfy some IID premise of law of large numbers. Now, to do integration, all you need are sequences which are good for integration. You don't care about the IID features. You don't care about that. That's interesting when you think about it. Now, the idea of quasi-Monte Carlo methods is to explicitly construct a sequence that's designed to be good for integration. But this is going to take some thinking, some serious math. But you figure that the human mind should be able to do better than mindless random choices. Monte Carlo is really, using Monte Carlo methods is like saying, my brain is tired, I'm just not going to use it, so I'm going to let some random number generator, which of course isn't really a random number generator, do the job. And so there's some interesting comments about a random number generator, conventional random number generators. Anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. I like that one. Also remember what pseudo means in pseudo random number generators. Pseudo means fake, feigned, false, spurious, counterfeit, illusory. Very good. So the thing is, at least the phrase pseudo-random is honest. Now then, and so it makes a law of large numbers, nothing applies because they're not really random. Now, what you will hear a lot of from Monte Carlo propagandists is, oh, the best deterministic methods converge at a rate of n to the minus 1 over d, where d is a dimension. Oh, but Monte Carlo will converge at the rate of 1 over square root n for any dimension d. So then they say, well, for high dimensional problems, you've got to use Monte Carlo. Well, first of all, this is all bogus because every implementation of Monte Carlo uses deterministic sequences instead of random numbers. So any theorem that applies to deterministic methods also applies to pseudo-random sequences and methods based on that. So, so Monte Carlo can't escape these theorems. No, okay. Okay. Now the fact is, experimental fact is that when you use these things to compute integrals, you do observe that they converge at, the error converges to 0 at the rate 1 over root n. Well, why? How did that happen? So apparently there does exist deterministic methods for doing integration in a sampling method, which converge at rate 1 over n, 1 over square root n for any dimension d. So anyway, math using Monte Carlo propaganda logic, 1/2 equals 1 over d for any d bigger than 1. Anyway, there's a variety of things you can conclude from this. I remember in one of my mathematical logic courses, a professor would love to start with, well, assume the theorem isn't true, and then he'd do some arguments and calculations, etc., and then he'd conclude that 0 equals 1. And then he said, well, gee, how'd I get here? Well, it's because he assumed the theorem that he was trying to prove was wrong. Apparently the theorem is true. So anyway, so that's proof by contradiction. Anyway, so and Monte Carlo propaganda gives you all sorts of opportunities to twist them around. Now, by the way, when they say that the best deterministic methods, when they talk about what numerical analysis theory says, they say the best deterministic methods converge at rate 1 over n to the d. No, n to the minus 1 over d. They use worst case analysis. That means there do exist some functions, given any method, deterministic method, there exists some sequence of functions such that the error goes down very slowly. Whereas with Monte Carlo, when they say Monte Carlo rates converge at rate 1 over root n, they're talking about on average. Then, because I can easily come up with a function such that Monte Carlo methods, or sequence of functions such that Monte Carlo method doesn't work at all. So if you did worst case analysis on Monte Carlo, you get the error is n to the 0. There's no convergence. So anyway, this is all the propaganda from Monte Carlo people is just propaganda. You can't believe it. You know, it's like listening to the Trump briefings on the coronavirus every afternoon here. So here's the fact. There are deterministic methods that do much better than Monte Carlo asymptotically. They've been used for many high dimensional problems. So they're good. Now okay, I'm gonna take you in the next 15 minutes to take you through some basic concepts. A sequence is equidistributed over AB if when you take the first little n elements of that sequence, evaluate f at those points. So this is like a sample approximation of the integral. And then as n goes to infinity, as you go through the sequence, in the limit, you will converge to the true integral. And that this is true for all Riemann integrable f. So this is a tough game. It's like I put down a sequence xj, and then nature can put down a function f. But basically, if you put down the sequence xj correctly, any function that is Riemann integrable that nature chooses in this game, this approach will still work. And in general, there's this, you can do an n-dimensional version of this. Now, how do you get such a sequence? Well, it's very hard to come up with them. It turns out that here's one that really works nicely. You take an irrational number theta, and then you take the nth, you're going to draw points on 0, 1. And so the nth draw is going to be take n times this irrational number, and then you truncate the integral part, and you just get the fractional part. So this is new notation. Wiggly brackets, x wiggly brackets is the fractional part of x. Okay, you just lop off everything to the left of the decimal point. Now, this sequence is equidistributed. Now, the function that we're talking about is where basically if here's your current, if xn is here, then xn plus 1 is here. This has slope 1. This may seem like, oh, this doesn't look like it's going to be too good, but it does. But here's an example. Here's your first 1,500 vial points. Now, that actually looks close to being a uniform sample of points. Compare this to 1,500 random points. Which one would you rather use to compute an integral over the unit square? I think this one is far better than this one. Many years ago, 25 years ago roughly, I was a discussant of a paper that John Gevicke was giving, surveying Monte Carlo methods in econometrics. And so this was taken from a slide there. I said, well, here's 1,500 random points in unit square. Here's 1,500 quasi Monte Carlo points. So which would you rather do? And so he responded somewhat. Here are some other examples. Here's an example of an n-dimensional formula for n-dimensional vial points, Haber points, Niederreiter, blah, blah, blah. Anyway, there's. variety of these. These are very simple versions. And so for n dimension, what this means that when you have n dimensions, or d dimensions, sorry, d dimensions, you pick d prime numbers, different prime numbers, and then the nth, you take the square root of each, which is going to be an irrational number now. And then the nth draw is going to take basically n times this vector and then take the fractional part of each component. And then the Haber sequence, they all use something like similar to this. These things are not serially uncorrelated. They kind of have the form of the linear congruential multiplier approach, but yeah, it doesn't. But yeah, it's very different. Now we have the concept of measures of deviation from uniformity for sets of points. Basically, suppose you have a set of points, let's say a scatter of points in the unit square. What you want to do is measure just how close it is to being uniform. And now let's say this is discrepancy in one dimension. What you do is you take all possible intervals between 0 and 1, a, b. And now the integral of 1 between 0 and 1 over that interval should be b minus a. Now, if you're just doing a sample, then basically the integral is going to be how many points are in the interval a, b, and are these set points divided by n. And so this is now you do this over all possible intervals, and that gives you a measure of discrepancy. And so then if you have a sequence, you also then look at the discrepancy of the truncated sequences. Now, basically on 0, 1, the problem is trivial. The lowest discrepancy is just a uniform set of points. That's not surprising. Now then, if you did in d dimensions a tensor product of those one-dimensional intervals, what you'd find is that their discrepancy is ordered of n to the -1 over d. However, we can do much, much better. You can read the fancy math if you want, but the thing is that tensor products of points are bad. Now, here's some more theory. I'm not going to spend time on that, but here's an example of, suppose you had this integral to compute. Now notice, what is this integral? Well, in each dimension, you take 4 times x sub j minus 2. You take the absolute value of that, and then you sum those absolute values and divide by d over them. Then you integrate that function over the unit interval. I think I is 0, 1, yeah. So this is going to be a function with multidimensional kinks, not something nice to integrate. Suppose you are 10 dimensions and you have 1,000 points. The integration, I took a Monte Carlo sequence, and the error was 10 to the minus, looks good. It looks like I did a decent job of 10 to the minus 3. See, now 1 parenthesis minus 3 parenthesis means 1 times the power of 10 to the power of -3. So this is nice. Error is like 0.001. But when I did the Weil sequence, the error is like 0.0003. Haber is also, you got basic, the error is down the 4th digit, neither right or same. And now if I did 10,000, 1,000 thousands as a million, the Monte Carlo thing does. Now notice that, by the way, when I go from 10 to 1,000, I'm multiplying the sample size by 100, which means that the error should go down by a factor of 10, which it does. But notice that the while, the error for the while sequence goes down by a factor of 100 because its convergence rate is 1 over n. Also, Niederreiter does a good job. Haber is generally not as good in that respect until you get large sets. Now we go to 40 dimensions, and there again we see that Monte Carlo is beaten by these other methods. And now we have something that's a very wiggly kind of function. And Monte Carlo just is disgraceful for 40 dimensions. While actually, the Weil doesn't do well either, but the Niederreiter set of points does seem to have nice convergence properties. So again, you do not have to derive these things. There are tables for these. I have, in my book, I have some tables of examples of these. Now, this slide is, there is some very fancy theory behind some of this. I'm not going to get into it. Now, you might say, okay, you do this quasi Monte Carlo thing, but the nice thing about Monte Carlo stuff is that it has errors, but gee, you can estimate the errors, you can estimate the variance of these things. Because suppose I do an integral by Monte Carlo, and then I get a value, but then I'm wondering just how much randomness there is. Well, I could do it 4 more times. And now I take the mean of those 5 cases, and I get my approximation of the integral. And then I take the variance across, the sample variance across, and now I have a measure of the error of the Monte Carlo approach. And you say, well, that's great, that's wonderful. I don't need to know any theory. I just need to crank away randomness, 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 do 5 samples. They better be different samples, but 5 different samples, independent samples. And then I get not only a good approximation of the integral, but I also have an approximation of its variance. What more could you want? And quasi Monte Carlo, how are you going to demonstrate that the integral that quasi Monte Carlo gave you is a good one? How are you going to estimate its errors? And when they say these things, they think I'm going to go back to these kind of theorems and show off this math. No, no, no. What am I going to do to do? I say no, no, no. You have 1,000 points in your Monte Carlo thing, and then you do it 4 more times, so you have a 5,000 draw. You have a mean and an estimate of the variance. Good. What I can do is I can take 1,000 quasi Monte Carlo points, and then I can do a random rotation of those points. And that rotation will give me another set of quasi Monte Carlo points that are just as good as the first one, but randomly different. And I do that rotation 4 times. Now I also have 5 estimates. They are also going to be, and because the rotation is random, it's going to be kind of like doing a Monte Carlo thing, but I'm going to have 5 numbers. I'm going to have a mean, and I'm going to have a variance. My variance is going to be much smaller than yours, the Monte Carlo people. So quasi Monte Carlo, there's really never any excuse for using Monte Carlo, because with quasi Monte Carlo, I say never any excuse, okay, if you're doing Monte Carlo, Markov chain Monte Carlo, then the dimensionality is enormous, and Monte Carlo is the only way to go. But if you're just doing dimensions, let's say 10 or 20 or even 100, there's quasi Monte Carlo schemes to do that. And then, and they are going to be asymptotically superior, and the error estimate that can be done is just as good, just as valid, and robust. So anyway, that, boy, ending up pretty good time here now. So that is the situation here for integration. There are the classical integration rules that I showed you. based on, first of all, Newton cotes and then their product rules. And then there's the orthogonal polynomials, their numerical integration rules, which are much more powerful. And then, of course, there's a tensor product approach to that. I gave some allusion to monomial formulas. That's something that I don't anticipate you needing during this course, but I just want to alert you to it. Then I talked about Monte Carlo things, described about some basic Monte Carlo kinds of simulation ideas for computing integrals. And then the quasi-Monte Carlo stuff, which is vastly superior. Now, you might wonder, why don't people use quasi-Monte Carlo? Well, one thing is that economists don't read applied math stuff. But a more fair point to make is the following. Quasi-Monte Carlo sequences are far superior to Monte Carlo sequences asymptotically. Asymptotically, as the sample size grows to infinity, they are far superior. The problem with quasi-Monte Carlo sequences is that there's a burn-in phase. Now, people will tell you that any random number generator also has a burn-in phase, but with random number generators, you throw out, let's say, like the first 100 draws, then you're pretty confident that you've got a sequence that does what you hope it will do. And so you can get by with sample size. Samples of 1,000, 10,000 are practical, and you can do. And people have been doing that stuff, well, in economics since the late 70s. A quasi-Monte Carlo in the late 70s would not have been very useful because they require a larger burn-in sample. It takes longer for a burn-in. And so basically, given the capacity of computers in the 70s, quasi-Monte Carlo wasn't practical. Well, that was 40 plus years ago. There's no excuse now for not using quasi-Monte Carlo sequences, because you can now easily draw 1 billion random variables, and at sizes of 1 billion, quasi-Monte Carlo just is enormously better than Monte Carlo. So again, that's a little history behind this. A little more history behind this is that I'm not going to talk about Markov chain Monte Carlo, but just a little history of it. Some of you may have seen or heard reference to a paper by Metropolis. And that leads to that there's methods called Metropolis-Hastings method. And that's because there's a paper by Hastings, and then I think earlier was a paper by Metropolis. Metropolis had 4 co-authors, however. The total citation is Metropolis, Rosenbluth, Teller, and Teller. The last Teller on that list was Ed Teller, who was a colleague of mine at the Hoover Institution. So a colleague of mine at the Hoover Institution sowed the seeds that now leads to today's MC methods. Okay, so that's it for the official lecture. Let me do a countdown for my use later. 5, 4, 3, 2, 1.